Good afternoon, class. The next reaction of carbonyl compounds that I would like to talk about is what we call the nucleophilic conjugate addition or the beta addition. The basis of this reaction is the electrophilic character of the beta carbon. So this is our alpha carbon and this is our beta carbon. And due to the inductive effect of the carbonyl group over the conjugated system, the beta carbon possesses an electrophilic character. So this beta carbon is a weak electrophile. In fact, its mesomeric structure, when this carbonyl group is activated by Lewis acid or Bronsted acid, it would assume a mesomeric structure like this, shown here, showing a full positive charge of the beta carbon upon activation. The general mechanism of nucleophilic conjugate addition or beta addition is shown in the following. The first mechanism for nucleophilic conjugate addition is an acid catalyzed reaction. In this case, we may use a Lewis acid or a Bronsted acid. So this Bronsted acid will protonate our carbonyl oxygen here to form a protonated species, this one. And this could assume another resonance form that has a full positive charge at the beta carbon, this one. And now our nucleophile will attack this position to assume the next structure. And in the next structure, the conjugate base will deprotonate the hydrogen of the weak nucleophile to get rid of the positive one formal charge that is on the nucleophilic atom. And finally, this subsequently forms this structure here, the enol structure, which undergoes tautomerism, and it finally yields this product in which the nucleophile attaches at the beta position. Okay, the second reaction mechanism for this type of reaction, for the beta or conjugate addition, is done in basic conditions. So what we have here is our enol structure, which is directly added with a strong nucleophile. The strong nucleophile will attack the beta position. Afterwards, it will form an enolate structure, and the enolate will react with a hydrogen ion source to finally form the final product, which is in which the nucleophile now attaches at the beta position. Nucleophilic conjugate addition or beta addition is much relevant in the context of what we call the Michael addition. Michael addition is the reaction of a diketone or diester with an enone. Okay, so what happens here is that suppose we have a diketone. This one is our diketone and our enone. So our diketone has many alpha hydrogens here. We have the red alpha hydrogens and the green alpha hydrogens. So these alpha hydrogens have different pKa values, but the most acidic of these alpha hydrogens is the green one. It has a pKa of 9 for the reason that upon deprotonation of the alpha hydrogen, it would assume three resonance forms. One is the carbon ion, the other one is an enolate at the left position, and the other one is an enolate at the right position. So it has three resonance forms, and for that reason, this alpha hydrogen is the most acidic of them all. So in Michael addition, we have a diketone reacted with an enone in the presence of a strong base such as sodium hydroxide or sodium alkoxide or any metal hydroxide and metal alkoxide, as long as it is a strong base, to form this type of product. So the mechanism for this reaction is that we have our strong base reacting with the most acidic alpha hydrogen, which is the green one. So remember, the most acidic is the one that is reacted first, and this reaction will release methanol in the background. Next is the formation of the carbon ion. So this is our carbon ion, which is a nucleophilic. It's a strong nucleophile. This carbon ion can assume two more resonance structures, which are enolate. So this is a carbon ion, and the other structures are enolate. It has three resonance forms, and for that reason, this intermediate is a very stable intermediate. Now, this nucleophile would attack our electrophile, which is the beta carbon of the enone. So this is our electrophile, and this is our strong nucleophile. Now, it will attack the beta carbon, which is electrophilic, pushing this pi electron and subsequently pushing the pi electron of the carbon double bond oxygen or the carbonyl group to yield this structure here. Okay, so remember, the enone is bonded to carbon number 3 of our diketone because the nucleophilic site is the carbon number 3. Now, methanol, which was previously released, becomes hydrogen ion source, which reacts with our enolate. So our enolate reacts with that of our hydrogen ion source, abstracting the methanol and finally producing this triketone product. So this is our product afterwards. Basically, this is the essence of Michael addition. Let's have some more examples about Michael addition. Say for example, we have a diester for that matter. Okay, this diester is reacted with an enone structure. So say for example, we have an enone structure here. Okay, this is our enone, and this is the electrophilic site of the enone. And it is done in the presence of a strong base such as a strong base is, say for example, we have sodium tertiary butoxide. This will form this type of product afterwards. Okay, so this is the product that is formed by this type of reaction. The mechanism of this reaction is shown here. So we have tertiary butoxide, a strong base reacting with our diketone, diester, forming this type of intermediate. So it can form a carbon ion intermediate or an enolate intermediate. We could form a carbon ion here or an enolate. It can assume many other resonance forms. Okay, these are the resonance forms of the intermediate, and this will react with our electrophile. So our electrophilic site is a beta carbon here, and it is reacted with our nucleophile. So what happens here is that this pi electron is moved over there to form this type of product. Okay, the product is an enolate first, but we have a hydrogen ion source which is tertiary butanol or 2,2-dimethyl propan 2-ol. This will form the final product which is shown here in this figure. Okay, so this is the essence of Michael addition. Now you might wonder, why is it that there are two electrophilic sites in an enone? We also have this electrophilic site, but the beta carbon, which is an electrophilic site, is the one that is being reacted. So the reason for that is this position is what we call a soft acid in the context of HSAB theory. And this one, having many different resonance structures, also serve as a soft nucleophile. Okay, so when you encounter this topic in your advanced in organic chemistry, please make sure to consult your professor about hard and soft acids and bases. One more example of beta addition is the alkylation of enones. Okay, the alkylation of enones is done through two ways. One is through the use of Grignard agent, or what we call Grignard reaction, and the other way is by using Gilmander agent. First one is the use of Grignard agent. Say for example, we have this type of enone. Remember, this electrophilic site is hard electrophilic site for the reason that this one being an electrophile is related to the charge density of the carbonyl group. Okay, it's a hard electrophile and it is being reacted with also a hard nucleophile from Grignard agent. So Grignard agent, say for example, we have methyl magnesium bromide. Now, what we have here is a hard nucleophile for the reason that it has a very high charge density. So the negative charge is localized in the methyl group, in the carbon of the methyl group. This methyl carbon ion is also what we call in HSAB theory, it's what we call is a hard base. Hard and hard will react together and soft will also react together. So what happens here is that the hard nucleophile will attack the hard electrophilic site to form a alkoxide intermediate product. This one. And finally, upon addition of water, which is our hydrogen ion source, we form an alcohol product like this. Okay, so this is in the context of Grignard reaction. Basically, this is not beta addition or not conjugate addition. So what I would like to underscore is the reaction of Gilmander agent. So Gilmander agent is made through the reaction of alkyl lithiums with copper iodide. So what we have here are alkyl lithiums. Alkyl lithiums are sources of very strong bases or what we call carbon ions. See, examples of alkyl lithium are we have tertiary butyl lithium, which is a very strong base. This bond is borderline ionic, so we may also represent tertiary butyl lithium as something like this. This carbon ion is a very strong base. Now, how are Gilmander agents prepared? So Gilmander agents are prepared through the reaction of alkyl lithiums, these are what we call alkyl lithiums, with copper iodide or cuprous iodide. Okay, so the reaction of alkyl lithium with that of cuprous iodide will form Gilmander agent. So we have an alkyl lithium or this one with cuprous iodide. Okay, what is formed from this one is we have our copper is now bonded to two carbon ions or two alkyl groups to yield a negative charge, and it will have a counter ion which is lithium. This is what we call Gilmander agent. So Gilmander agent is represented by this type of representation R2CuLi. Okay, this is what we call the Gilmander agent. Okay, so what's so special about the Gilmander agent? Okay, the Gilmander agent is it's what we call a soft electrophile, a soft nucleophile, for the reason that this copper ion only becomes nucleophilic because of an extra alkyl group that bonded to it. So what happened in this reaction is that we have an alkyl group replacing the iodide first. We have an alkyl group replacing the iodide first, and copper here has a zero overall charge, but then copper can still accommodate another carbon ion, alkyl carbon ion, because of its d orbital. And there are some spaces in its d orbital which can accommodate another alkyl carbon ion to form a dialkylated copper complex which bears a negative 1 formal charge. So now we have nucleophilic copper atom here, but this negative 1 formal charge is not due to its own electron pair being donated, but it's because of the extra carbon ion bonded to it. In this context, this copper is the copper in Gilmander agent is being regarded as a soft nucleophile. So now being a soft nucleophile, it bonds to that of the soft electrophilic site of our enone. So in Gilmander agent, in the reaction of Gilmander agent, so we have a Gilmander agent here, R2CuLi plus, reacting to an enone. Okay, so remember this is a soft electrophilic site and this is a soft nucleophile. So what happens here is that copper will bond to the beta carbon in what we call the beta addition or the conjugate addition to form this complex. Okay, so what we have here is copper, an alkyl group bonded to it. What happens afterwards is that due to the increase of electron cloud to copper atom, remember copper here is a cuprous ion which is copper 1, and it normally it only wants to bond with another anion. So normally it would bond to another anion to form copper 1 product. Say for example we have cuprous bromide, but we force it to have two bonding, and now it has three bonds all in all. Okay, so what happens here is that copper has been forced to the corner, so it doesn't want more bonding anymore. So copper now undergoes what they call the reductive elimination. So reductive elimination is the concept that I have taught to you previously when we reviewed about organometallic chemistry. So reductive elimination is when a metal will decrease its oxidation state and only bond with a fewer number of ligands. A hypervalent metal atom will reduce its oxidation state to only bond with a few number of atoms. The analogy that I have provided to you before is suppose we have this copper atom attracted to another atom, so it bonds with that another atom, after but surrounding the copper atoms are also atoms that are attracted to it. So it's like, okay, this one has a crush on R, but some other R are also interested to copper, so it bonds with copper. So now copper has two partners, the two R's, and after bonding with another R group or alkyl group, it now has three partners. So three partners are more than what copper could ask for. So it is quite daunting to it already. So it decided to break off its bond with the two of them and only focus with one of its bonded atoms. So that was the analogy that I have provided to you before about reductive elimination. So a reductive elimination here is it happens to both two of the R groups. So these two R groups will bond instead as copper and one of its partner leaves away. So this one leaves and these two R group will bond together. So what bonds here are you have this R group and this we have this R group and the other R group. Finally, we have this type of product. We have an enolate here and we have a hydrogen ion source to form this product afterwards. Okay, so let's have a specific example about reaction of Gilmander agent. Okay, say for example we have copper bonded with isopropyl and reacted to this enone. Okay, the product of this reaction is this one, but the reaction mechanism will be something like this. We have copper, then have isopropyl group, and what happens here is reductive elimination. Reductive elimination will cause this isopropyl group to shift there. And finally, upon addition of hydrogen ion source such as water, we have this enolate reacting with our hydrogen ion source to form the product afterwards. So this is the essence of beta addition or conjugate addition to enones. We have a special reaction here combining beta addition or conjugate addition, aldol condensation, which involves aldol reaction and E1CB reaction, and that is what we call the Robinson annihilation. So please remember this type of reaction. The Robinson annihilation is one of the most important reactions in organic chemistry because we could make polycyclic compounds from Robinson annihilation reaction. So the essence of Robinson annihilation is having our aldol donor. So this is our aldol donor. I mean, having our Michael donor. So the Michael donor is the one that adds to the beta position and reacting to the Michael acceptor to form the Michael product. Okay, so the first step of Robinson annihilation is the deprotonation of the alpha hydrogen. This is deprotonated by our base to form an enolate. So basically it is enolization, basic enolization reaction to form this enolate structure, which is a nucleophile, a strong nucleophile at this position. Now we have this beta position here acting as an electrophile. So it reacts with our Michael acceptor to form the Michael product. Okay, so remember, after reaction with ethoxide base with the alpha hydrogen, what is produced afterwards is ethanol. And at the stage where the Michael product is formed, we also have an enolate here. So our enolate will abstract the hydrogen from ethanol to form this product here. So as the enolate abstracts this hydrogen from ethanol, what is formed is an ethoxide, which is a strong base, and that ethoxide will deprotonate this alpha hydrogen from here, producing an enolate structure. So another enolate structure is produced here, and this enolate structure is nucleophilic at this position. Now, what happens afterwards is that this enolate will perform an intramolecular aldol reaction. So there's what they call an intramolecular aldol reaction. We have an enolate, which is an aldol donor, and this carbonyl group as an aldol acceptor. So an intramolecular aldol reaction occurs. And remember, in order to count the proper number of atoms that are part of the ring, because it's intramolecular, so a ring is formed afterwards, we have to count the number of atoms that are in the ring. So we have 1, 2, 3, 4, 5, and 6. Okay, so therefore we have to draw a 6-membered ring. So now we have here 1, 2, 3, 4, 5, and 6 based from our previous numbering. Okay, so what is formed here is an alkoxide intermediate, and this alkoxide intermediate will abstract the hydrogen of ethanol. Okay, so ethanol is formed here, and now that hydrogen of ethanol has been abstracted once again by the alkoxide to form an ethoxide and this product here. And what happens afterwards is that this ethoxide will act as a Bronson base to abstract this alpha hydrogen here to form another ethanol molecule. And finally, an E1CB reaction occurs. So we have an E1CB is followed after this reaction. So this final step is what we call an E1CB reaction, breaking up this bond between carbon and oxygen. Even though it's not polarizable, it could still break the bond between carbon and oxygen, and finally producing this Robinson annihilation product. Okay, this complex Robinson annihilation product can further be used to make more complex polycyclic structures. So in synthetic organic chemistry, Robinson annihilation is also used to prepare or to synthesize pharmaceutical agents or pharmaceutical drugs in the laboratory. So that is how important Robinson annihilation is. But at its very core, what happens in Robinson annihilation is basically we have beta addition or nucleophilic beta addition or conjugate addition followed by aldol condensation reaction. So aldol condensation, as we have all learned, is basically aldol reaction and E1CB elimination or dehydration of the beta hydroxy, the hydroxyl group at the beta position. So that is what we call the Robinson annihilation. Okay, the last final reactions that I would like to introduce to you are the miscellaneous reactions of carbonyl compounds. Okay, we have two miscellaneous reactions that I would like to underscore. The first one is the Wittig reaction. The Wittig reaction converts aldehydes and ketones to alkenes. And in the Wittig reaction, we have our aldehyde and ketone, aldehyde or ketone, reacted to what we call a phosphorus ylide. So this is what we call a phosphorus ylide. As we examine the phosphorus ylide, we have a phosphorus here, doubly bonded to carbon. But this could have a resonance structure in which the phosphorus has a positive charge and the carbon has a negative charge. So basically, the phosphorus here is electrophilic and the carbon is nucleophilic. So being electrophile and nucleophile at the same time, it can react to our carbonyl group through this type of arrow forming mechanism. Okay, so basically, this very strained intermediate is formed afterwards. It's four-membered intermediate, which is very strained, is formed, and because it's a very strained intermediate, therefore this intermediate is very unstable. So it is not a long-lived intermediate. It will break down its sigma bonds like this to finally form this product. So the other product produced here is a triphenylphosphine product. This one. This shows the conversion of aldehydes and ketones to alkene through what we call the Wittig reaction. You remember, Wittig reaction always use phosphorus ylide. Okay, another reaction that I would like to show you, or I would like to talk about, is the Wolff-Kishner reaction. So the Wolff-Kishner reaction converts aldehydes and ketones to alkane. So if the Wittig reaction converts aldehydes and ketones to alkene, the Wolff-Kishner converts them to alkane. So what happens here is that hydrazine, this molecule, is being reacted to aldehydes and ketones. So hydrazine or any amino group has a very relatively strong nucleophilic nitrogen. So this nitrogen is borderline strong nucleophile. So it attacks this electrophilic center of your carbonyl group to form this alkoxide intermediate. So our alkoxide intermediate is a strong base, so it can obstruct. But by the way, this reaction occurs in the presence of potassium hydroxide and ethylene glycol or ethane 1,2-diol. So this alkoxide will obstruct the hydrogen of your alcohol, of your ethylene glycol, to form this type of product here. So it now becomes an alcohol, now becomes an hydroxyl group, but this hydroxy functional group can also function as a bronzed base to deprotonate this adjacent hydrogen of your ammonium ion. So this ammonium ion will be reacted by the hydroxy functional group to form this product. Now, remember what is formed here is water, and water is a very good living group. So this bond is very polarizable. Now, what happens here is that the nitrogen will push its lone pair to release water and forming this type of iminium cation intermediate. And remember that the hydrogen of an iminium cation intermediate is also acidic. So the pKa of hydrogen is around 9 to 10, and it could be reacted by a strong base in the background. So the strong base is either the hydroxide or the alkoxide from the ethylene glycol. Now, what is formed afterwards is this structure. Okay, this intermediate could be reacted by a strong base in the background. So this hydrogen is reacted by the strong base in the background, and the sigma bond is broken to be converted to pi electron and pushing this pi electron here. Now this pi electron becomes a non-bonding electron or a lone pair. Now it becomes a carbon ion, which is a strong base for that matter. And this carbon ion will attack the hydrogen of water or the hydrogen of the alcohol in the ethylene glycol to produce hydroxide afterwards. And this product. So we have compound number 2 here produced afterwards. And what happens next is the abstraction of this hydrogen by your hydroxide to subsequently produce nitrogen and breaking up this bond. Okay, so why is this process spontaneous, or what is the driving force of this step? The driving force of this step is the release of nitrogen gas afterwards, and that release of nitrogen gas is entropically favorable. So delta S is increased after this step. So the delta S is positive, so therefore this step is also favorable. Now, after the release of nitrogen gas, we have nitrogen is N triple bond N here. So this sigma bond here now becomes a non-bonding electron or a lone pair, and now it acts as a carbon ion. And this carbon ion is a strong base which reacts another hydrogen in the background from water or from the alcohol to finally produce alkane product. Okay, so let's have a more specific example of this one. Okay, say for example we have cyclohexanone. Cyclohexanone is converted to alkene through the reaction with hydrazine, potassium hydroxide, and ethylene glycol. Okay, so what happens here is that it is converted to alkane afterwards, but the reaction mechanism is like this. We have this one first, and we have alcohol in the background, ethylene from ethylene glycol, and we have this hydroxyl group taking the hydrogen of the ammonium group we have here, forming water, and we have this lone pair of nitrogen pushing away water and releasing it afterwards to form this imine structure. So carbon double bond nitrogen is what we call an imine. This one is an iminium ion because it is an ionic molecule. This one is an iminium ion. But carbon double bond nitrogen is what we call an imine functional group. So this iminium cation has an acidic hydrogen here, which can be reacted by the alkoxide to produce this type of structure. So we have this structure afterwards. And remember that this strong base can also deprotonate this hydrogen of the nitrogen here. Or I think it would be much easier to visualize that. Say for example, if this lone pair pushes this pi bond over there, okay, so we have a very acidic part here, so that okay, the base can deprotonate that one. Now after deprotonation, we also have formation of this intermediate, and we have a carbon ion here reacting with alcohol or water for that matter. A strong base deprotonating this hydrogen to release nitrogen afterwards. N2 is released. And what we have here is we have a carbon ion which reacts to a hydrogen ion source. It could be water or it could be the alcohol from the background to form the final product, which is an alkane product. Okay, so this is the essence of Wolff-Kishner reaction. Okay, to summarize, okay, the last part of our discussion involves nucleophilic conjugate addition or nucleophilic beta addition. So nucleophilic conjugate addition, nucleophilic beta addition is the addition of nucleophile to the beta carbon of an enone. So this is our beta carbon, and the beta carbon is partially positive. So a nucleophile adds to this position. Okay, so a nucleophile adds to this position to form an enolate. Okay, so we have a nucleophile now bonded to the beta position to form an enolate structure, and this enolate will react to a hydrogen ion source to produce this product afterwards. There are two examples of beta addition reactions that I have shown to you. The first one is the context of Michael addition. In Michael addition, we have diketone or diester added to an enone. So diketone and diester is what we call the Michael donor because it serves as the nucleophile. And the enone is what we call the Michael acceptor. So what happens here is that we have a diketone or diester in which this central hydrogen here is the one that is being deprotonated by the base for the reason that it forms three resonance structures. So the resulting intermediate structure is very stable because it has three resonance forms. So we have this carbon ion resonance form, we have the enolate resonance, one enolate resonance form and another enolate resonance form. Now, these three resonance forms are the Michael donor, and they form a bond with the Michael acceptor, which is the enone. So suppose this is our Michael acceptor, and it is reacted with the Michael donor to form this type of product afterwards. Okay, so this product will react with a hydrogen ion source. This is an enolate to form the final product of the Michael addition. So we form the Michael product afterwards. The Michael product will be a triketone structure. Okay, so this is the Michael product that is produced by this type of reaction. Okay, the second type of beta addition reaction that I have shown to you is a reaction of Gilmander agent. Okay, so Gilmander agent has this canonical structure reacted with any enone. This reaction will form a beta addition product like this, but the reaction mechanism will be addition of the copper to the beta carbon to produce this copper complex. Okay, so this copper complex will have copper surrounded by high electron density, which makes copper crumble down to perform reductive elimination. So we have reductive elimination here, and copper will choose only one partner, leaving these two alkyl group together. So what is formed afterwards is this alkyl group is bonded there. We have an enolate structure here, and finally addition of a hydrogen ion source will produce the final product. The hydrogen will now be here. Okay, so that was the end reaction for Gilmander agent. So the last example that I have provided for beta addition is the Robinson annihilation. Okay, the Robinson annihilation is basically composed of three steps. The first one is beta addition, followed by aldol addition, intermolecular, and finally we have E1CB elimination. So we have intramolecular aldol addition here, and finally E1CB elimination. Now for the miscellaneous reactions, I have introduced two miscellaneous reactions. The first one is the Vatic reaction, which converts aldehydes and ketones to it converts aldehydes and ketones to alkene. So say for example, we have an aldehyde reacted to a phosphorus ylide. Say for example, we have this type of phosphorus ylide. Now, the resulting product would be something like this. Okay, another reaction, miscellaneous reaction that I have introduced to you is the Wolff-Kishner reaction. The Wolff-Kishner reaction involves addition of hydrazine to your aldehyde and ketone to yield an iminium cation, and finally we have subsequent steps will release the nitrogen, which is an entropically favorable step to form the alkane product afterwards. See, suppose we have an aldehyde or ketone here reacted with hydrazine, the presence of potassium hydroxide and ethylene glycol. Okay, this will produce an alkane product. Okay, so that is the end of our discussion about carbonyl chemistry.